with the lectures from now on till 8 o'clock. I like to talk with you about the projects and the topics and your objectives. So actually I like that those groups that are here, I like that each group with their team members come here and talk with me for a few minutes because I like to get their topics and write it down and see what they are, because we really need to start on that, because you need to get some more information. Once I know the topic, then I can give you some material sources so you can use it for your project. And then you need to make a little plan that, plan among yourself that who should do what, and plan for the time that which day we should be ready for what, because don't forget that soon you will be invited for your 50% presentation. That is not very far, it's like the end of next week. So after we finish this week, then the end of next week will be the time that you need to present your 50% work. So this is why I'm, not really pushing you, but I'm just reminding you to do something about it. So which group is ready to share with me their
created them throughout the geological life of every places, mainly starting from mountainous areas with small rills and small streams. Then they get together, they create little bigger channels, and they go to different types of rivers. It is called mountainous river, it is called ephemeral river, it is called incest river, and alluvial river, and so on, depending on where in the land is located. When those river gets very close to the ocean, they cause some sort of mountain meanderings. When it is between that flat area and the mountains, they are called sort of ephemeral, which means that one river section has got many small channels that they are separating and joining together. But in the mountainous areas, they are mainly like single small channels. The mountainous area very steep, very rough. In the middle area, it's less steep, but it's still steep and with more like rounded boulders. When it goes to flatter areas, then it is very fine sand and clay and silt, plus the land is so flat that these rivers sort of start meandering. Anyhow, those are natural type of rivers that we are dealing with, but what we are going to discuss today is the design of artificial canals that we are interested. Now, I'm going to start with these types of channels with the information in the book that you already have a copy, which is called Concise Hydraulics. And if you see in there, it says the main purpose of a canal is to convey the water from one point to another point in most cost-effective way and in a safe way. When they say in a safe way, it means when we are talking about man-made canals, or on line. Line, it means like you use some type of material to cover the bed and banks, like concrete, like some type of geotextile, or simply by putting some sort of a stone, whatever you think you need to do that. So that is some type of lining.
when you are not lining it, then it is the natural material that forms the bed and the sides or the walls of the canals. So when you design the canals one way or another, on one hand, this is an economical thing to do, and from a technical point of view, you have to design it properly. That means that the most important thing in the canals are the velocity. So your velocity should not be a velocity to scour the bed and banks if this is not lined canals. What is it? So in these notes, we are going to simply see the problem from a hydraulics point of view, and then I will give you other notes that you can see how to design the other types of canals or channels. But let me also mention that from hydraulics point of view, when you want to know whether the canal is scouring, eroding, or not, there are a number of different theories. For example, in one case, you might just use the velocity as a parameter to control the sedimentation and scouring. This method is more empirical. This is based on experiments and field tests, and which means that always it may not give you a good result, especially if you don't have good geotechnical information about the type of earth and material that you are going to build the canal from. But there is another method that is called tractive force, which means that when the water is flowing in the canal, at the bottom and the two sides of the canal, the water itself will create a shear stress on those beds and banks. Okay? Now, if you calculate the shear stress from, your canal cross section and the depth of the flow in the canal, then for certain materials that you want to line the canal or you don't want to line it, there are information about that permissible shear stress, that if this is this material, if the flow and the cross section that you selected does not cause a shear stress, a tractive force bigger than the resisting shear stress, then the canal that you are designing should be okay, right? If the water is causing a shear stress, shear resistance from the material in the bed and banks, then in that case, the water will scour that, okay? We will later see and also see some example with what we are going to do here with these things. First of all, when you design a canal, whatever the flow depth, the water depth that you will have in the canal, that is simply because sometimes there may be a wave in this canal, especially if you are dealing with hydropower canals. Remember that we talked about surge tank and the waves in the surge tank and in the tunnel and so on. In this case, if this is like a canal and there is a canal, the water is going to somewhere and then it gets into a penstock. Now in this case, this is, if I draw a cross section, it could be anything like this, or it could be like this, some sort of open channel type. And then the water level in the reservoir maybe in that level. Now if there is an instantaneous opening or closing in the turbine, we don't have a surge tank, but you may get some waves here. So if you don't put a good freeboard for this, the water will overflow from these banks, you know. So you need to, you get something 4.24. I have a feeling that this is a mistake. It might be 2 square 2, but anyhow. And in this other one, it is deeper, only 0.5 meter wide and 4 meter depth. Now this cross section and all these other cross section are almost equal, or actually equal. So in terms of excavation, the amount or the volume of material that you are excavating is the same, but in actual reality, the amount of money that you are going to need an equipment to dig 4 meters deep, while this other one is only 1 meter deep. So cost-wise, I don't think that the excavation is the same, but the amount of material, the volume of material that you excavate is the same. Now, in here there is one important parameter, K, which is called conveyance factor. What is that conveyance factor? If you change the Manning's equation in this form, if you remember the other day I mentioned that if you change the Manning's coefficient, equation from this form, this is like the general form that everyone normally uses, but in here instead of R, they have used A over P. So if you solve this for, if you replace R with A over P, then you get the equation that is on the board there. And then what they do, they call this A to the power of 5 over 3, a square root of S, and N divided by N. They call this K, conveyance factor. And if you see, for this particular case, which, this is an explanation of how you design a best hydraulic section. So A is not changing. For the 3 cases, right by 4, you get a bigger Q, because the conveyance is the same for all of them. If you divide it by 4.24, it becomes smaller. If you divide it by 8.5, then the flow will become smaller, which means that for the same amount of work, if you select this cross section, you convey more water. If you select that cross section, you convey less water. So even from economics point of view, if you think about it, you will say, well, this first cross section looks more economical, doesn't it? Because with the same excavation, although the cost of the excavation will not be exactly the same, but assuming if they are the same, then for case A, for that cross section, you can convey more water. Simply because the conveyance factor is the same, but the width perimeter is different. So the smallest or the smaller width perimeter can convey more water. So this is good to know, because anytime that you wanted to design a canal from hydraulics point of view, you can select many different cross sections. You can select excuse me. You can select a parabolic one, you can select a trapezoidal one, you can select a rectangular one, or whatever. So by this simple calculation, you can believe the hydraulics is concerned. Any question about what we discussed, which in a way was the repetition of a few other things that we had before? Is this clear to everyone? Very clear, or just a little clear? Who didn't understand it? Everybody understood? So very good, I'm really happy. Flexible lining. We did not discuss that type of canals just before, because I will come to that a little bit later, but I want to discuss this concept, which is really a better one, more scientific, and a better way of designing. Even you can design line channels or non-line channels, but this is like a more scientific way to deal with this. You can read these, whatever the description is. Now this is nothing but the same Manning's equation. This alpha is nothing but a conversion factor that if we use the SI unit, this alpha is equal to 1, like I wrote 1 over n and so on. This was for an SI unit. But if you calculate the shear stress, whatever that number is, then you may say, I multiply this by 1.5. Why? Because you think that probably something happened, that there will be a bigger shear stress due to the flow on the wall and bits of the canal. And therefore, that means that if you have, let's say, like we talked about 2 Newton per cubic meter, if that is what you get from calculation, whatever safety factor you use, let's say 1.5, you multiply that by 1.5. So 2 becomes 3, right? Now you select a material that can stand 3 Newton per square meter or something bigger. So this is what it means by safety factor in this case. This flow chart is nothing but just a calculation procedure of how you do it. I am interested in this example. Now, see how this example is done. They say evaluate a proposed gravel mulch lining on a trapezoidal channel for a stability. So what is given? The flow is 0.42 cubic meter per second. The bottom of this canal is 0.4 meters. Z, one of the parameters of the slope, at the side is 3. And the bed slope of the channel is 0.008 meter per meter. And they also give us D50, one of the geotechnical size information as D50 to be 25 millimeters.
how to protection the environment.
I didn't get it. How do?
When coming a lightweight on the in-stock segment, but if lightweight, some unexpected material, some wood, something.
Oh yeah, right. Well, light materials will not have big impact. Again, this is a good point that you mentioned, because when you do these sedimentation tanks, besides those things that I mentioned, a specific gravity is also important. So a specific gravity, if it is sand, it's about 2.65. If it is something clay or something, it is less than that. But if you are talking about wood or those things, well, for those things, if they have big sizes, they shouldn't be able to go, because besides this, there also may be a rack here, you know. A screen of this type of sizes, that you need to include that in your hydraulic calculation to see how much energy is lost as a local loss through this rack. Okay? We will talk about that also one day to see how we can calculate. Because those big objects, like a big piece of wood, should not be able to go through this section. But on the other hand, if there are small pieces of wood going through, because the specific gravity of that is much smaller than sand and other things, it should not really make a big problem. But bigger sizes should not go through. So, and then when you add this also somewhere in the system, that everything needs to go through, that means that in the system you have another element that you need to calculate the local loss. Because if you don't calculate, then water passes through that. At the penstock, at the turbines, the amount of head that we are expecting is not really that much. It may be a little bit, but still, you know, these little by little adds together and they make the final head loss, and then you have to subtract that from the gross head loss in order to get the net head, which produces electricity. If you do this example, as an exercise, it doesn't really matter what type of section you are using. I just wanted to do the methodology. So this could be a triangle section, or this could also be part of a trapezoidal section. So if you just go through those equations and calculate them, and then we'll go down to see what else is there. So then you will see how to do these things. And so you can get a piece of paper and the pen and work this simple case. You will get some assignments to work. You can work either in the class in the afternoon, or you go home and you do those. But I like to get them back, you know. When I give you something, I like to get it back on Monday, you know. So both assignments for Saturday and Sunday is due back on Monday. Why Monday? Because you have time Saturday afternoon and Sunday afternoon. Because if you cannot bring it on Monday, then you will not be able to do it the rest of the week, because you will get busy. You go to work from the morning to late afternoon, and then you come here again, you will not have time. So those assignments are mainly for Saturday and Sunday afternoons. And if you don't want to do assignment, then we can, do some more things in the class here. It's up to you. Can you take the derivative of that section? If you don't, then you need to sort of review your mathematics from old days, Let me be back.